welcome. I still see people coming, so... Right, the topic today is the computer science behind a modern distributed data store. And that is, of course, a vast topic which I cannot even hope to cover in its entirety. So therefore, I have concentrated on 5 somewhat unrelated topics, but in the end you will see the picture come together. One is resilience and consensus. That is essentially about agreeing things in a distributed system. One is about sorting, a big classic in computer science. The next is log-structured merge trees. This sounds a bit more special. Well, it is, but it's used in many modern data stores. Then there's an odd one called clocks. That's about clock skew and synchronizing clocks and stuff. And finally, I will briefly touch distributed transaction, which is kind of the holy grail of a distributed data store. Right, so let's start with one of them. Essentially, the bottom line of this is to come up with a good implementation for a modern data store. What you have to do is you have to use modern computer science. These days, data stores are distributed. I think the time of a very, very large database on a very, very large computer, and that's it, is basically over because of various reasons. First of all, you want to scale out. You want to use multiple cheap machines to work together as one compute cluster and as one data store. And you want to be resilient because computers fail, and the more you use them, the more computers you use, the higher the likelihood that one of them will fail. And if you run a large cluster, then nearly every week a machine will fail. So, in a distributed system, you have to make things agree. There's no point in this side of your cluster believing the truth of your data is one and this side another. Things have to agree. And consensus is the technical term for essentially the art to achieve this kind of agreeing on things as well as possible in software. That's actually not too hard as long as things are good. You have a network, you can communicate, you can send copies of data easily over the network to another machine, and you know they agree on the same things. It's a bit harder, actually quite a bit harder, if things don't go so well. If your network has an outage, if your network sometimes drops packages, or delays packages, or duplicates messages, if your disks fail, if some machines fail and come back with corrupt data, and if some complete rack fails, or even if a complete data center fails. You might say, this is all rare, it doesn't happen. Well, it does. And if so, you are pretty much lost if the different replicas of your data don't match. So therefore, we need consensus in distributed systems, in particular in data stores. I haven't even talked about malicious attacks or enemy action here. It's just these nasty things which happen in every data center just because things break. Right. To solve this consensus problem, the traditional solution, well, traditional since 1998, is the so-called Paxos protocol. You might have heard about it, invented by Leslie Lamport. That's a famous achievement. More recently, there's another one called Raft, which was only devised in 2013. And the reason for that is essentially the following. Paxos is really challenging to understand. There are few people who would say that they have fully understand everything from the Paxos protocol. And even if they say it, they might not be right. And if you have looked into it, you can probably appreciate that it's complicated. There's a lot of variants of Paxos, which doesn't make it easier either. And therefore, in 2013, the Raft protocol was actually invented and designed to be understandable. That's a huge call for something as complicated as consensus. You know, we want to have a protocol here which is proven to be right. We just don't want to say, well, it seems to work. No, we want to have a mathematical proof that the protocol is right. And Raft has the properties, like Paxos, that it's a proven protocol, and still it is somewhat understandable. So if you are interested in consensus algorithms, here's my advice. Sometimes people don't want advice. Anyway, here's some advice as well. Have some fun to try to understand Paxos. There's very nicely written papers by Leslie Lamport and others, and it's fun to try to understand it. Don't implement it. That is not so much fun. It seems to be fun in the beginning, but to get it really right and working and fast and everything is really hard, in particular because the original papers don't tell you how to implement it. There's a lot of details for the implementation missing. Then, after you have appreciated the complexity of Paxos, then my advice is to look at Raft, because then you can actually enjoy the beauty and simplicity of it. But don't implement it either. It's also hard, although the Raft paper actually tells you quite a lot, not everything, but quite a lot what you need to actually implement it. I would advise you to use some battle-tested implementation which you trust, which works well, and which others have taken years of their life to debug. The most important thing, however, is that you don't try to invent your own consensus protocol thing. It's also fun, but it's even more difficult, and then to go through the whole procedure of mathematically proving it and making it watertight and having fast implementations, that's a huge amount of work. So unless you have, say, 5 years to do a PhD in computer science, then this might be a good idea to invent something like this, but other than that, I don't recommend that. I have some reason to give this advice because I've nearly tried all of this. I haven't tried to implement Paxos, but we did, for the database company I'm working for, we did an implementation of Raft for various reasons, and it was a lot of fun, and I think in the end we got it right, but it's nothing cheap. I have tried to invent my own, and I failed. Okay. Anyway, now let's try something other very difficult thing. I try to explain you what Raft is in one slide. Imagine you have 3 or 5, namely an odd number of servers, and you want them to agree on something as simple as a replicated log, say. Just to agree what is in this log, one step after another. You take an odd number of servers because you want to play democracy, and you want to use democracy to elect a leader. So amongst these 3 machines, they want to democratically elect a leader. Well, not really with a ballot, but something like one says, please elect me, and as long as he can convince a majority that he is the leader, well, that server is the leader for that term, whatever term means. So that's what they do, because the only person or the only server who can actually append something to the replicated log is the leader. That is the single point through which things have to go to establish a total order of events in that log. So only the leader can append. Now, obviously, you have to tell what happens if the leader fails. Well, if you have 3 machines, and you need at least 3 here, if the leader fails, then there are still 2 others. They can still form a majority, increase the term number, say, okay, we do the next election term, and one can say, please vote for me, the other can vote for him, and then they have a majority, and then they can move on without the previous leader, just in the next term of democracy. So therefore, appends only count when they have been replicated from the leader who decides about the append to a majority of persons, of nodes. So that is somehow a critical thing. You tell your append request to the leader, it appends it to its personal copy of the log, but that's not the point of time where it is really durable. Because if that leader fails, it might forget about this particular entry in the log. It's only when the leader has replicated it to at least one more machine that it actually counts as being committed. And then there's no way back, because whatever quorum can elect a leader, it must always contain one of these majority members, which have committed to that entry, and therefore it's persisted. Well, the whole protocol, I can't explain the details, the whole protocol has a lot of clever logic to ensure that there is just one leader, well, that's basically the majority idea, and that it can recover from failures. It can recover when there is a leader lost or when a follower lost, and so that's the tricky part. Now, even if you have all this set it out and have the paper and the analysis and everything, it's still a lot of fun to get right, in particular if you need high performance. Yeah? You can imagine that this is a complicated system. You want that it has a high throughput, low latency, and so on. But then, on the other hand, you have to observe the rules of the game laid out in that paper, because otherwise the mathematical proof that it's correct doesn't help. Usually, this is used in the following way. You have this replicated log, and the log entries are simply the changes to a key value store which is sitting on top. So you implement a key value store on top of this Raft protocol by saying all the changes are just put into this log. And then you have more fun if the changes of this key value store get out of hand. Then you at some stage you have to take snapshots of this key value store and compact them, and then you have to remove old log entries, otherwise you run out of disk space. And so there's a lot of stuff to get right, and surely I cannot really explain all this in one slide. However, there's a very nice demo by the actual inventor of Raft, Diogo Ngaro, and so I shamelessly steal this here just to show you the idea. Here's 5 servers, an odd number. So far, none is the leader, and here you see the 5 copies of the replicated log. Now, at some stage, one of them loses patience that we really should have a leader. This is the number 4 here at this stage. It has now said, elect me, and everybody has said, okay, you are the leader for term 2. And if now I tell this leader to add something to its replicated log, yes, sure enough, sooner or later everybody will have it, and as soon as the majority has it, this is confirmed to be in the replicated log. Let me just repeat that. Now, if I, for example, fail, and you can, the link is in the slides, and you can play with this yourself. If I fail this server, for example, then, well, it's just one less who replicates, and that's all fine. But if I fail this server here, which is the leader, then things stop. But sooner or later, one of these followers loses patience and said, we really should hear something from the leader. It's not coming. So here, server number 1 has taken over and has said, I should now be the leader. 2 others have agreed. That's an absolute majority. And so they are fine. Observe that all the entries are now written with term number 3. That's just the next elected term. And that has now precedence. And if I get back these servers online, eventually they will notice who's the leader now, will update their term, and will replicate entries, and in the end all is good. You can play around with this. It's a very, very nice visualization, and together with a very nicely written paper, if you want to understand what's going on with Raft, the paper, the description, and this simulation is very, very good. And it's already time for me to move on to the next big topic. I have about 10 minutes per topic, so therefore I have to rush on. Sorting. It's a very, very traditional topic in computer science, and surely it's very important for data stores because you need indexes, you need to find something, you need to be able to scan ranges and so on. In general, we need to sort things. This is now less referring to distributed systems, but what I say is somewhat relevant there as well. The problem is that with modern hardware, nearly all the sorting algorithms you find in the art of computer programming are rubbish. They are completely useless because the analysis isn't wrong. These analysis papers which have been written are mathematical papers. They are defined to be true, and there's no mistake in them. It's just that hardware has changed. These days, it's not the number of comparisons which limits your throughput in sorting. Rather, it's the data access. You have a machine with 32 cores and a lot of memory. You have a lot of data in the memory, in main memory to sort, and yet you cannot really keep your 32 cores busy because they cannot fetch the data fast enough from RAM if you use conventional sorting algorithms. And why is that? Well, when I was a kid, I was playing with a very old Apple machine, nowadays old. And if you compare the computation power from the time to my modern laptop, then the computation speed has increased by a factor of something like 20,000. The access, the single memory access latency, has only increased by a factor of 40. And in addition, at the time we had one processor core, now we have 32 cores, which makes it even worse. So the relative ratio of processing speed and memory access speed has got worse by a factor of something like 1280. So really, for such a modern machine, the problem is to get the data into the microprocessor and not to compare two things. So therefore, basically all the analysis of sorting algorithms is useless. So what can we do? Imagine you have 16 gigabyte of data and a 32-core machine. Everything is in memory. How do you sort this as quickly as possible? Well, here's the idea. One of the published algorithms is actually useful here, and that is Mergesort. So the idea of Mergesort is pretty simple. You sort regions of your, or a partition of your data. You sort this first, and then that, smaller pieces. And then you say, okay, I need to sort the whole thing, so I just merge all the sorted segments I have into one large sorted order. So the idea is basically, up here you have a bunch of sorted arrays, and you combine them into one. So the naive approach is easy. You take the first of each, take the smallest, and append it here. You take again the smallest of each, and so on. The problem is that then nearly every access is a cache miss, and your memory system just doesn't provide enough data for all your 32 cores to work. It's just not possible. You can maybe make one core busy to do that, and that's fine, but you can never use the power of your computer. So the idea here is to use a so-called min heap. That's an interesting data structure. It's essentially a binary tree which is balanced, so it's never very deep in any place. And the only condition is that whatever is in here, if you have a situation like this where there's a node and two subnodes, then the thing here must be larger than the two subnodes, according to the sorting order. And likewise, everywhere in the tree, this guy must be smaller than this and that. That's all, nothing else. And it turns out that inserting into such a heap and taking away the top and repairing the damage is actually a very fast operation. So the idea is that you make a heap which completely fits into your second level cache, say, or maybe even first level cache. And all you do is you take stuff from these guys here, obviously in batches, such that you have a few cache misses, and stuck them into this heap by following the heap rules. And then you take repeatedly the top off and put it in the result. So why is this good? First of all, since the top in this heap is always the smallest, if you have made sure that from everything you have something in the heap, then this must be the smallest of all, which you haven't processed yet. Then you get the right order here. So that's fine, correct result. But the point is, if you take a new item from here, well, yes, eventually you have to somehow have a cache miss, so you have to get it from main memory once. But then, when you put it into this heap, nearly all comparisons you have to do to sort it in the right place in the heap and to repair the heap structure are comparisons from second level cache. So therefore, in this way, you can make it so that all accesses to sort out this heap are from cache. And therefore, if you think about it, the whole business, if you parallelize this as good as you can, then you can keep all your processors busy, and all of their accesses are mostly from cache. And that is the crucial point to make it fast. Therefore, you cut your whole array into a lot of pieces. You apply first trivial local sort, as long as things are in cache. And then you start doing this to refine and combine to ever larger regions. Right in the end, you have to do some kind of control with your threads, and maybe you have some stuff which runs in only one thread. But in principle, you make sure with this idea that you have all accesses, or 99% of the accesses, not from main memory, but from cache. That's the only critical thing for the analysis of this algorithm. And then you can come up with an algorithm which actually has 32 cores, 99% CPU usage. And that is the best you can take out of your machine. Right, that's your sorting. Single machine, but very, very similar ideas happen if you have distributed data across a cluster and you need to establish a total sorting, total order. That's exactly the same thing. Now suddenly you have to make sure that all your accesses are local on the node and not remote over the network. And the very same ideas apply. Okay, on to the next one. Second 10-minute topic gone. Log-structured merge trees. Here we are talking basically about an implementation of some kind of data store on one machine. So think of some key value store, maybe sorted key value store, but on one machine still. Obviously, this is a building block into for the implementation of a larger key value store. So what do people expect from such a situation? Say you have a 16 gigabyte RAM machine and a 2 terabyte SSD attached. Well, you probably imagine that you are able to store as much data in there as your SSD can hold. So you don't want to be limited to RAM. And equally, you don't want to do just single accesses. They should be fast as well. But you probably want to allow for bulk inserts, and you would somehow expect that the data store can take as much data as your SSD can write per second, maybe a factor of 2 away or something like that. Furthermore, you would expect that you have very fast reads as long as you stay in some kind of hot set. So coming back to the example, say you have 2 terabytes of data, but you actually only access some kind of 10 gigabyte of it. Well, if you have a 16 gigabyte RAM, you would expect that this data store can mostly fetch things from RAM if they come from this hot set, and that things are particularly fast if you hit the hot set. Well, traditional B-tree-based structures often fail to deliver on at least one or maybe even 2 of the last points. So that's a problem. Yeah? So in particular, if you have a high write load, and if you have a particular hot set situation, then traditional data structures just don't don't fit what you need. So let me give you the idea of the so-called log-structured merge trees. So imagine a sorted key value store, sorted by key. The general idea is as follows. You have levels, 0, 1, 2. And essentially all you write to that data store first appears in level 0. And what you do is you use sorted chunks, which you first assemble in memory. So say you take 10 megabytes of writes and sort them in order in a memory table. And in memory you can easily sort and insert and maintain maybe a tree or whatever. And now you accumulate more and more of these guys. They might overlap because obviously you cannot control what is written to the database. And the idea is if you have, once you have enough of these, you combine some of these and merge sort them, essentially with the methods we had before, with the stuff on level 1. So you can imagine these chunks here to be something like 10 times as large as these, and this guy 10 times as large as this. And the major difference here is that they can overlap in level 0, but here you do all the smallest keys over here, such that this one here is smaller than the smallest in here, so that these areas don't overlap. So what you eventually do here is you write to level 0, and you trickle data down, and what you do is you essentially do merge sort. You take a bunch of these, merge sort them with the previous region here, and write a new version here. And likewise down here, if these get over full, then you take a bunch of these and merge sort them with down here, and so on with larger levels. So why is that? Why is this idea of only writing at the top and then trickling down with merge sort? First of all, merge sort works pretty well on modern machines, as I explained before. And secondly, your modern data disks, SSDs typically, but also spinning Rust disks, they really want to write sequentially. So they absolutely don't like if you put something here and then here and then here and so and do random writes. So what you want to do, and it's essentially a similar situation as with the cache awareness we had before, what you want to make is that essentially all your disk writes are sequential. Well, if you think about this system, if you assemble one of these guys in memory, then there's no problem. You can write it out sequentially to disk. And if you think about the merge sort, what you do is you pull in your data in batches in memory, pull pieces of that as well, and then you write the new version of this one with the merged results. But since you do a merge sort, you can also write sequentially. So that means that every one of these operations here leads to sequential write of large amounts of data on disk. And an additional benefit is here that since you only write up here, all these files are completely immutable. They are not changed at all. So the only thing that happens is that eventually this guy is replaced by its new version, which is a very quick operation. Then you can retire the old immutable file and have a new one, but you would only do this, of course, once you have written the new one. So that's the basic idea behind log-structured merge trees. They have pretty good properties. They are also not perfect, and you have to tune the parameters and so on. But let me give you an overview over what I essentially just said. The writes go into the top in some mem tables, and then are written sequentially out. All files, all these bunches here I had, are sorted and are mutable. They are once written in a linear fashion and then kept forever, or at some time discarded as a whole. Compaction, that's the process of taking some of these, merge sorting them one level down, and possibly throwing away old unused data. Can happen in the background. Obviously, there's still some implementation details to be sorted out to do this right, not to hinder new writes and so on. Anyway, that's what happens in the background. You can use merge sort, which is good on modern hardware, and all writes use sequential I/O. Right. Then there's another trick, which I explain here. This is about Bloom filters and cuckoo filters. So let me get back to the picture, because eventually it comes to reading. We've only talked about writing so far. Imagine you need some key. Where do you find it in this mess? Well, what you do is the following. You first look on the level 0, because if you write a new version of a key value pair, then it will appear on the top. And everything which is higher up in the levels, in smaller level numbers, is more current and overwrites everything below. If you find the key up here, fine. These are mostly either in memory or still in block cache, so that's not a big deal. Unfortunately, you have to search all of them because they can overlap. but everything is a binary search, or you use hash tables, that's all fine. Now, when it comes to not finding the key here, then obviously you have to go further down, because the key might be in some smaller level, or in some lower level with a higher number already. Fortunately, they don't overlap, so you only have to look into one of them. Let's say this, because you know the ranges. But here comes a problem. This is on disk. It might be large, and these, of course, even larger. So therefore, now you somehow have to do a binary search to find your stuff. And here comes the trick with the Bloom filters. A Bloom filter is a data structure which uses not a lot of memory in comparison to what it can do, and therefore can probably be cached in memory, and can tell you that a key in here is not in here. So imagine I'm looking for a key. The Bloom filter, I can ask the Bloom filter, is this key in here? And the Bloom filter can say yes or no. If the Bloom filter says no, it's 100% sure and secure that the key is not in there. If the Bloom filter says yes, then it's probably it's a maybe. So if the Bloom filter says yes, in most cases it will be in there, but in many cases also it might not be there. So what you do is you ask your Bloom filter first before you do an expensive seek on disk. The Bloom filter is supposed to be in memory. If it quickly says no, okay, then you know the key is not on this level, go on. If it says yes, it could be in here, then you actually look there at the potentially higher cost, but you might still hit a block cache. And so on. So you go from top to bottom, you use your Bloom filters, and therefore you can sometimes even not find the key very quickly. Now you see, the problem is, if you don't do this trick, then looking for a key and not finding it is very expensive, because you have to go through all the levels and look everywhere and fail everywhere and potentially miss a lot of caches. Anyway, that's the idea with Bloom filters. There's a more modern approach called cuckoo filters, which uses even less memory and has better properties with respect to not lying to you too often. But that's another interesting topic for a whole talk. Anyway, these log-structured merge trees, they give you good write throughput and reasonable read performance. And again, it's a matter of optimizing things. They are very, very popular. We use them because we use RocksDB, the RocksDB engine, but a lot of other databases use them, and potentially also other data techniques, but that's very, very popular these days. Okay, on to the next one, hybrid logical clocks. If you have a distributed system, and now we are really talking distributed systems, then, well, it's a matter of fact, your clocks will be not in sync. There's nothing much you can do about it. Even if you use the network time protocol, then you have to live with something like 20 milliseconds. You can bound somehow the clock skew, but it's there. Well, it's general relativity, which gives you fundamental limits to synchronicity. But in practice, we are not talking about general relativity. But even in one data center, you have clock skew between machines. Now, you would say, so what? Doesn't matter if the clock isn't completely correct. The problem here is the moment you take timestamps for whatever on different nodes and you want to compare them later. So why would you want to do that? You essentially want to know, if you look at timestamps, you want to know what happened first and what happened after. Yeah? Because the smaller time obviously is first. And for example, you might want to resolve conflicts. You have two different writes. You want to basically say the second one is the one that counts. Yeah? So you want to compare timestamps. Or you want to sort your log files, but the log files coming from different machines. You want to sort the log entries. You want to know what happens after another, obviously. And if you want to debug a distributed system and the log entries from different machines are not in chronological order, in real chronological order, because the clock skew happens, it's really hard to tell what's going on. You maybe want to detect network delays and measure things like this. You would want to do time to live things. Anyway, log entries, timestamps are useful, and you want to compare them. And we don't have them because of clock skew, so what can we do? Hybrid logical clocks are a neat trick which are useful in distributed systems to salvage a bit. So first what you do is, obviously every computer has a local clock, and you use network time protocol to basically synchronize them, so you don't have a clock skew of 5 minutes or so. But then you still have these nasty 20 milliseconds, so what can we do about that? What really matters is not any odd timestamp. What you really want is that if you have causality between two events, so something happened because of something else, then for debugging purposes and for conflict resolution and for whatever, you basically want that a timestamp taken with a cause is smaller than a timestamp taken for the effect. If you have causality in the other direction with your timestamps, then you are in trouble. So what is causality in a distributed system? Essentially, there can only be causality between two events on different machines if a message has been passed from machine A to machine B. There can only be an effect on B which is triggered by a cause on A if there has been a message from A to B. That's the idea. So what we do is the following. We have a local clock which says some kind of time. And furthermore, with every single message in the system we send along, we send a timestamp. So whenever I send a message from server A to server B, I first take a timestamp on A and send it along, just on principle. So therefore, whenever there is causality between two events, a timestamp has been transported from the cause to the effect. And now, if I'm asked to take a timestamp on any machine, I look at the local clock and I actually return the maximum of the local clock and any other timestamp I've ever seen. That is, if you send me a message and I get your timestamp and I later should derive a timestamp of my own, I look at my clock and look at the maximum of all the messages I received and I return the maximum. So why is that good? First of all, causality is preserved. If an event happens on machine A with some timestamp, and then a message is sent to B, again, there's a timestamp sent along, and then on server B, I take another timestamp. This other timestamp will always be larger than the one I had in the first place because of this message being sent. So therefore, whenever there is causality, the timestamp of the event, of the effect, is larger than the timestamp of the cause. And finally, imagine all messages stop, then obviously my local time will always catch up with whatever maximum timestamp I've seen. So therefore, these clock values are not just logical clock values. I could just do kind of counting, but what I really want is that they somehow still resemble actual time. And so the good thing here is that when there's no more message being received, then eventually I will actually return the timestamp which is on my clock. So the idea is if you have a distributed system, you need to compare timestamps from different machines. You play this hybrid logical clock game. It's really not difficult to implement. You just have to send a timestamp along with every single message. And whenever you send a message, you take a timestamp, send it along. Whenever you receive a message, you take note of the timestamp you get and compute the maximum of everything you have seen. And whenever you take a timestamp, you take the maximum between what you've seen and your local clock. There's a very nice description of this, which I have linked down here. So obviously, it's an obvious comment. I've basically not invented any of what I'm presenting here. So therefore, I'm just reporting about results from clever people. Let's come to the final topic. I have 12 minutes left, which is obviously not enough to talk about distributed transactions. So therefore, the only thing I can possibly achieve is to tell you what the problem is and why it might be difficult. And difficult it is. If you talk about transactions, you usually are in the context of good old-fashioned, good old transactional relational databases on one machine. Could be a large machine, but on one machine. And you are playing the ACID game. So that's an acronym, and A stands for atomic. So if you have a transaction on such a data store, you want that this transaction is either executed in its entirety or not at all. So if something goes wrong in the middle of the transaction, you would rather have it not be done at all than to have it done halfway. So that's your atomicity. If you read with a transaction, you would like to see a consistent state. You would, for every other transaction in the system, which might be ongoing, you want to see the state either before that transaction or after, nothing in between. So if I write in a transaction 3 different key value pairs, say, what I want for every other transaction is that they either see my 3 values or nothing at all of these writes. So that's your consistency, and which is actually a different type of consistency as in replication. Isolation is essentially a similar thing. If you have 2 transactions going on at the same time, you want that neither sees the other. It's only that you want to see a transaction if it has been committed, and you want only transactions to see that transaction, that the first one, if it happens after, if it starts after the first one has committed. There's different isolation levels, but for this talk here, this doesn't really matter. And the other thing is, what you want is durability. If you write something to a database, and the database says, yes, I have written, then you want that it stays written and doesn't vanish just because some machine fails. Now, let's look at what this all means in a distributed system. You see, on one machine, it's all pretty easy. You are in the same process. You can do this isolation business. You can make sure that when a transaction runs and it doesn't complete, then you do everything back. You can make sure that it's only visible to the right amount of transactions. You can make sure that if it says it is written, then it has been written to local disk and so on. You can actually trust this result, and so that's all doable. It's not easy, but it has been done for 30 years, and relational databases are very good at doing this. Now, in a distributed system, imagine a system with 100 machines which make up your data store, and you can send transactions to any one of them, and they can be executed. You expect that they can take as many transactions as you can send to 100 machines. You expect that it can store as much data as 100 machines. Now, how do these 4 principles look like now? Atomicity. You do changes here and there, but obviously you have to shard your data. So the data is distributed. There is some replication going on, but still some of the data is here, some of the data is here. You do change different things in one transaction. How do you make sure that the machines agree on whether this transaction has committed or not? So here we have a consensus problem as to whether the transaction has committed or not. Now, if you want a consistent snapshot of your data, you want to do a backup at 12 o'clock, how do you make sure that you see a consistent set of values across all your machines, even if it takes a lot of time to take it out? So consistency is a problem in a distributed system. How about isolation? You do changes here and there and that, but there's another transaction going on which reads here and there, and you have to make sure that it either sees all these other changes or not. How do you do that? And finally, how do you solve the durability problem if any node can vanish at any time? So the point is, all four of these are considerably more difficult to get right in a distributed system. And the only possibility is that you actually replicate data. If you don't replicate data, you cannot hope for durability in the presence of failures. You need to think about resilience. You need to define what kind of failures your system should sustain and still work in an ACID fashion. And you need to make sure that you do the right amount of failover if you observe that one machine has now finally failed. If you look at the database market, you notice that there is a lot of distributed databases which don't do ACID. Yeah, a lot of these NoSQL databases and these databases which came up as a replacement for relational data stores, or maybe not as a replacement, but as a solution for special cases, all of them don't do distributed transactions. And we at ArangoDB, so far in the published version, don't do distributed transactions because it is really hard to implement. However, in the past few years, there have actually come up a few distributed data stores which offer this or the other ACID guarantee in a distributed fashion. So one should mention Spanner, that's probably groundbreaking, which is not open source, so we don't really know how it's implemented. Then there's FoundationDB, which used to be closed source. It essentially vanished because it was bought by Apple, but recently it was open source, just 2 weeks ago or so. There's CockroachDB, which is open source and which promises a relational data store, which is fully transactional and distributed. And we at ArangoDB also want to go this route. We want to implement distributed transactions. We have a plan, but we are just working on it. So if you look at just the number of data stores which do distributed and transactions and which don't, then the overwhelming majority doesn't do it. Most, or basically all relational data stores do ACID transactions, but just on a single server. So the problem really comes with the distribution. Right. I have 4 minutes left, and I hope I have convinced you that distributed transactions are hard. So I want to use the remaining 4 minutes to basically give you an idea how one could possibly approach this problem. Whenever you do transactions and you want isolation, you probably have to store multiple revisions of your data items. Simply because if somebody writes a key value pair, say, or a row in a table or whatever, and then overwrites that later with a transaction, then you still need the old value. You need the old and the new value because some other transaction might have been started so early that it has to see the old value. Another new transaction might already see the second value, and you might have multiple values over time. So therefore, it's a really no-brainer. You need to store multiple revisions of rows, of key value pairs, of whatever. And that is called multi-version concurrency control. So it's multi-version because you keep multiple versions of your data items, and concurrency control because you control which transactions are running in a concurrent way. Now, if you do writes in a distributed data store, obviously you have to distribute your data, otherwise you can't scale out. You have to do replication because you can lose machines and then you want to still have the data. So therefore, you have to do all these things, and yet you have to somehow make sure that there is a single point in the system which decides whether or not a certain transaction has committed or not. And you have to make sure that that switch for every single transaction is somewhere persisted. It must be a scalable system such that you can run multiple transactions. This very switch has to be replicated as well. So again, you need consensus about the copies of that switch. And it has to be resilient in case of a machine fails. You don't lose the information as to whether the transaction has committed. And that is essentially the problem. You have to make sure that for every single transaction you have such a place or whatever arrangement that you can tell now or later whether the transaction has committed, and it has to be durable. And then you have to make sure that everybody is aware of this fact and follows the rules. I have only 2 minutes left, so therefore there's not much more I can say about this. There's a lot of literature. I recommend the Spanner paper. I recommend everything CockroachDB has written. We haven't written very much so far, but it's a very interesting and nice topic and very complicated, and I think the database market is moving towards more distributed transaction data stores. So I think the next few years will be very interesting to watch and to see, because client programming against a transactional data store is so much easier and prettier than without transactions, that I think this is going to be there. So I stop here. I've put a few links. I will put up the slides somewhere on the conference site, and I'm happy to answer your questions. Yes?
One question here about the log merge structure.
Yeah, log structure merge trees, yeah.
Yeah, so you mentioned that the zeros level is entirely in memory. How does that affect durability, and yeah, how do we handle that?
Yeah, let me quickly repeat the question about log structured merge trees. I've indicated that the top is all in memory, so how can we have durability? I think I was unclear here. You keep it in memory to read it very fast, or you keep at least a cache of that in memory, but you still, once such a block is complete, you still write it to durable storage. Yeah, so it's both in memory and there for very quick read access, but also for durability. Yes?
For many systems, we've implemented that, and you can use journaling techniques, you can use all kinds of things to keep that in-memory block with the right image journaling to back it up. So I think there are methods to provide that durability in the event of an unexpected event, machine failure, whatever.
Yeah. Yeah, yeah.
In Raft, when you have a server fail, you then have an even number of servers. What happens if you get an even split of those?
Yeah, the question is, in Raft, if one server fails, you suddenly have an even number. How can you maintain majority then? The thing is, without without tricks, which are actually not in the Raft paper, you keep the total number of servers always at 3. So you still have a majority, has to be 2. That is, you need both remaining servers to act. So you don't say, now we are a democracy with 2 people. You still say we are a democracy of 3, and one is just absent. Yeah, here's another question.
Might be a bit detailed. So in the Mergesort, you mentioned about caching, and I was wondering that if we use as a block size the cache line, and we use a regular method, then only the first access will be a cache miss, right? And then all the other operations will be cache hits, because they will be brought in the cache.
It depends. So the question is, if I just use a regular method and have the block size a cache line, then all should be good. I don't think this is the case. If you, for example, take a quicksort, even if you run it on cache lines, it will jump all over the place.
No, I mean, if you still use Mergesort, but without the binary, the regular Mergesort.
If you use Mergesort on cache lines, then still most of your... Well, it probably depends on how many blocks you merge.
Yeah, yeah.
If you merge not too many...
If we say we merge, for example, five parts,
yeah.
the cache contains 5 cache lines, and we set the block in one cache line.
Yeah, you would still probably fetch a new one. You have to compare it to 4 others. They might be in cache, but you still have 20% cache misses, which ruins your day. Let's discuss the details after the talk. I think we have to stop. Thank you very much. I'm still around, so you can also ask questions.